अच्छा जनाब, ठीक है, ऑल आर म्यूटेड और लेट्स स्टार्ट लेट्स स्टार्ट बाय शेयरिंग द स्क्रीन। ठीक है जनाब, दिस इज आवर चैप्टर 2। ठीक है जनाब, तो दिस इज द आर्टिकल इन विच वी आर यूजिंग द एक्चुएशन, वी वर स्टडिंग एक्चुएटर्स एंड एक्चुएटर्स में हमने बेसिकली प्राइमरीली देखा था, मेनली जो हमारे पास था दैट वाज पीजोइलेक्ट्रिक क्रिस्टल्स, और पीजोइलेक्ट्रिक क्रिस्टल्स हैं, शेप मेमोरी एलॉयज हैं। ठीक है, तो ये बेसिकली माइक्रो एक्चुएटर्स हमने देखे थे। द मोस्ट इंपॉर्टेंट वन अमंग ऑल दीज इज बेसिकली दी electrostatic one. The beauty of this electrostatic one actuator is that we can use it for the actuator as well as sensor, right? जो actuating principle है, that principle is basically the Coulomb's law. ठीक है, Coulomb's law says कि if you have two charged particle A and B and having the respective charges of Q and Q dash and having a distance of r between these two charges, so there will be an attractive or a repulsive force depending upon the charges. We know that positive charges always repel each other, whereas opposite charges always attract each other. So if they are opposite charges, so they will attract each other, and if they are similar charges, so they will repel each other. So whatsoever that is, there will be a force. That force may be an attractive force, or that force may be an repulsive force. So that force is equal to 1 over 4 epsilon q dash over r square. So Coulomb law says the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them, right? E is basically the permittivity of the medium, which is generally 8.8 10 to the minus 12 coulomb per Newton meter square, and or 8.85 picofarad per meter in vacuum, that is epsilon naught, right? And R is the distance between the particle. So more the charges between the two, more will be the force, lesser the distance, higher will be the force, because of attractive force or electrostatic force is inversely proportional to the distance between them, right? So now we have two plates. One is this one is this plate, one is this one, and one is this one, right? And their length is L and their width is this one. That this is the length and this is the width, right? So now the induced capacitance we know is epsilon or epsilon d A over D, area over the distance between them. So this is the gap between them, and you have the area, right? So C epsilon or epsilon D epsilon naught A over D will be the capacitance that will be generated between them. A is basically the overlapped area, right? The area of that particular area that is overlapped by both one, and D is that just gap between these two plates, just like a capacitor. It is just like a capacitor. So area means W into L, and this is, by the way, the overlapped area, right? Overlapped area is W into L, whatsoever that is. Supposingly this length is 10, width is 10, so 100 meters square will be the area, right? But that is the total area of the plate. In capacitance, that is the overlapped area. For example, if that is length out of 10, 7 millimeter length, and out of width 6 millimeter length is width is covered, so there will be 56 square that the area will be. So this is the overlapped area. This A is basically the overlapped area,
Sure, sir.
right? So epsilon R epsilon naught will be W into L divided by D, right? Now this is basically the capacitance. So there is some charge as well, that is Q, right? So energy associated with the electric potential is half, and Q we know is CV, right? And integral of that with respect to V, that will be potential energy, that is U, and that will be half CV square, right? You will take the derivative of CV, so it will be half CV square, and we know what the CV is. So half epsilon naught epsilon not W over L over WL over D into V square. So now the normal induced normal force is curly U by curly D, means partial derivative of U with respect to D. And with respect to D will be, here is the D, rest all will be constant. These all will be constant except D, and D is 1 over D, right? So when you will take the derivative of 1 over D, it will be D square with the minus sign, right? So it FD reduced normal force will be half epsilon R epsilon naught WL over D square V square, right? So means this is very important expression for us. This all is very important. Reason behind, whenever we calculate the electrostatic force, whenever we calculate the electrostatic force because of these two plates, it will be equivalent to this whole expression. Now see, if you want to increase the force, so either you have to increase the overlapped area WL, or you have to increase the applied voltage that is being applied over here between the two plates to generate some capacitance, or you can decrease the gap. So these are three parameters on which the force, electrostatic force, generally depends: overlapped area, applied voltage, and the gap, right? So you can manipulate accordingly to, if you want to increase or decrease the force accordingly for your design, right? Any confusion?
No, sir.
Good. Acha janab. Now, since we are talking about the two parallel plates, right? So there could be two options. Either this overlapped area may be in the direction of the length or in the direction of the width, right? For example, if the force is in, if the overlapped area is in the direction of the width, so FW, force in the direction of width, will be independent of the width. This is the same expression we saw in the previous slide, right? FW is minus half epsilon naught epsilon R L over D V square, right? Or, and when the force is in the, when the overlapped is in the direction of the length, right? So that will be independent from the length. The expression will be independent of the length. FL, force in the direction of this length, force in the direction of this length will be FL minus half epsilon naught epsilon R W over D V square. So these are, so because we can look into that, how you can see my video.
Yes, sir.
Okay, so this is what they are saying. If this is length and this is width, so overlap could be either in this direction or it could be in this direction. So this is again an overlap and this is again an overlap, right? So if this is length, so and this will be overlapped in the direction of the length, right? So we will take FL, and that FL will be independent from the width of that, and this will be the FW. I mean, this is again different overlapped area, but in the direction
Yes.
of W. So
Yes.
FW, force in the direction of the width, will be independent from the length,
Width.
independent from the width. So
Width.
FL will be equals to minus half ER E naught W over D V square, and FW will be minus half ER epsilon or epsilon naught L over D into V square, right?
Yes, sir.
Chalo,
Yes, sir.
good. So now stopping the video. So now application of this electrostatic actuator is in the micro gripper, right? So now you can see there are two electrodes over here. This is one electrode and this is another electrode here, right? So when you apply the voltage against this, so these are the two electrodes. These are just like the two plates. Electrostatic force will be there. When electrostatic force will be there, so it will be attracted. When they will attract each other, so these two jaws will gradually close, right? Likewise, if you have these two plates, these are now in a different format, right? You can
Yes.
see over here, this is the gap closing. In this, gap will be changing, and in this, the overlapped area will be changing. It will move into this direction. So when they will move up and down, so overlapped area will change. In this particular format, gap will be changing, right? So both are, again, we have just discussed that irrespective के आपका overlap area बढ़ता है या gap कम होता है, both can cause the electrostatic change in capacitance, and that change in capacitance can be utilized for sensing, or they can be, because force will be there, so they will force the two plates to move towards each other, so they can use as an actuator. So here they are using actuator. So when they will move into, sorry, not in this direction, it will move in this direction. So when they will move in this direction, the jaws will again close. So this is how you can utilize these gap closing. This is called gap closing, and this is called overlap wearing. Overlap wearing. हमसे को वो लेक्चर ले रहे हैं, तो थोड़ी देर तक बात करते हैं अंकल। वो अभी बाबा असल में एक ऑनलाइन लेक्चर दे रहे हैं ना, तो ठीक है वो कह रहे बाद में कॉल कर लीजिएगा। ठीक है ठीक है जनाब। तो we can use these electrostatic actuators for the micro grippers. Another format of the electric, that is the comb drive, right? This is the very popular comb drive because these are the fingers. These are looks like a finger, so they are assumed to be a comb drive. So comb drive is a very interesting sort of mechanism. As I already said, that the comb drives or the capacitive mechanisms or electrostatic mechanisms can be utilized for both actuation as well as sensing, right? So comb drive is an actuator, very interesting actuator. Interesting in terms, it can be used as an actuator, and it can be used at the same time as an as an sensor as well. So and very easy to make it using the fabrication techniques, general fabrication techniques, and physics is very well explored. So most of the time we rely on these sort of actuators. So very good actuators, physics is known, easy to design, easy to fabricate. So that's why you will mostly see that most of the MEMS devices are based on these electrostatic actuators, right? Although force is very less, but where you don't need much force, so you can utilize this very easily by applying certain amount of the voltages, right? So if you see in this particular one, when again when they will when the voltage will be applied on this particular, these are the stationary combs, and sorry, drive arms and the closure arms, and this is, yes, this is the these are, this is basically fixed one, and these are moving one, right? These two, this one and these are the two moving one, right? So when voltage will be applied over here, so what will happen? When voltage will be applied, electrostatic force will be there. When the electrostatic force will be there, they will attract these two combs with each other, because this will be stationary, it can't move, but these are the moving, so they will move towards it into this direction, right? Into this direction. So again, overlap bearing will comb drives is there, and when they will move into this direction, this jaw will be, this jaw will be closing, having the distance of 10 micrometer, right? So number of electrode pairs, these are called electrode. It has different diameter, digitated comb drives, and electrodes, right? So these have different names, but most popular one is the is basically the comp drives, right? So number of this is the graph between number of the electrode pair. So this is one pair, this is one pair, this is one pair, and then again these are one pairs. These are all capacitors, right? These are all pairs. So number of electrode pairs or required voltages to operate, right? So as the number of electrode pairs are increasing, you can see that voltage, applied voltage is being dropped, right? So as the number of the pairs, and you can keep on increasing the number of the fingers, in other words, into a comp drive, you need lesser voltage for the actuation, right? So drastic reduction in the required actuation voltage with increase of number of the pairs of the electrodes, right? So they keep, and then definitely force will be multiplying, factor will be, force will be increased as the number of electrodes will be increased, as well as uh, as well as capacitance will also be net, or the cumulative capacitance will also be increased as these electrodes, because these are the number of, these are the capacitors. So if you keep on increasing the electrodes, so you, in other words, you are keep on increasing the capacitors, and thus capacitors keep on increasing, so capacitance again keep on increasing, right? Now another application is basically application of the micro actuations, right? Micro actuations, and these are the microphones. So what is the microphones? This is basically the pressurized equalization hole, and this is the cavity, and you have a membrane on it, right? Not the membrane on it. This is basically the back plate in which you have different holes, and this is on the top one. This is basically the diaphragm. ठीक है, this is diaphragm, this is the back plate having holes, and this is basically the cavity in it, right? So when sound waves comes on this diaphragm, it oscillates this diaphragm, so it vibrates. As it vibrates, the gap, air gap between this and this one, this decreases accordingly, right? When this decreases, so air pressure is generated. That air pressure goes through these holes, and when they go through this hole, a sound effect is produced, right? So this is how this miniature microphone acts, right? So this is 20 log 10 P over P naught. P is the air pressure in pascals, and P is the reference pressure. Reference pressure is over here, P naught, and P is being generated by this diaphragm. So 20 log 10 is basically the one which you can calculate, which can be calculated to calculate the noise level that is being generated by these one. The most microphones are designed for 20 to 80 dBs in the frequency range of 150 to 100 hertz. So the frequency, definitely this is a long theory. The frequency mainly depends upon the this diaphragm. What sort of frequencies you are interested to generate, so you make this diaphragm accordingly. So you can see what is the particular frequency range of the sound you are interested in. Obviously, for low frequency, you need, for lower frequencies or the human sound frequencies you want to listen, so you can go for that particular range. Or if you are interested in the ultrasonic frequencies, so you can go for those ultrasonic frequencies accordingly, and then you apply different electrical techniques to calculate and to evaluate the signals quality, and then accordingly sound is produced. A major challenge in MEMS microphone design and manufacturing is the packaging and integrated of MEMS and CMOS integrated circuits for the signal conditioning and the processing. This is one of the challenges you can have. Another type of microactuator is micromotors, right? It is very interesting. I mean, you have two electrodes. One is fixed set of the electrodes here in this one. This is the fixed electrode set, and this is the moving electrode set, right? But the pitch is set in a way that if a width of A is W, right? So in the fixed electrode, they have fixed pitch. Mean this is W, 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 and this is the constant one in a fixed set of electrodes. But in the moving electrode, that this one, you have similar size of the electrode, that is W, but the distance between the two consecutive electrodes A and B will be W plus W by 3. One, you have added an additional distance or additional gap of W by 3. If supposedly if it was W was equal to 3, so this gap will be 4. The 3 plus 3 by 3 is 1, so 3 plus 1 will be 4. So this will be 3 and this will be 4. But here this all is supposedly 3, right? So what happens? Again, when you will apply a differential voltage on it, when you apply a differential voltage on this set of AA, so this has a different, that you have different overlapped area, right? This is the overlapped area between these two, right? So when the voltage will be applied, electrostatic force will be generated. This electrostatic force will pull this towards it, right? Because this is fixed, this is moving, so it will move into this direction, right? As this direction as is moved into this direction, so A and A becomes overlapped, they become aligned, right? But at that particular instance time, because the gap between A and B is different from the gap between A dash and B dash is different from the gap between A and B. So what will happen? So at that particular instant of time when they A and A are aligned, B and B dash will be misaligned. So then you will apply the voltage on it. So they will again attract each other, and when they become aligned, right? So C and C dash will be misaligned. And then you will apply the voltage on C and C dash. So they will attract because of the electrostatic force. And this is how it keep on going and it keep on rotating, right? So how quickly that will be aligning and misaligning, that will depend upon the frequency. With which the frequency of the AC voltage you are applying on it. The higher the frequency, the quicker they will align and quicker will be the rotation accordingly for that particular motor, right? So this is how it, so one is lining, rest of the misaligning, one is lining, rest is misaligning, right? So in this way, aligning and misaligning keep on going and it keeps on rotating and moving. That was a linear motor, by the way, and this is the rotary motor. Again, you can see this or this aligned, but rest all are misaligned. So when voltage will be applied, so electrostatic force will generate and this will attract this, and when they become aligned, rest all will be misaligned. So they'll keep on attracting aligned and misaligned rotor stators and rotors. So the stator will keep, obviously stator will stationary there, but the rotor will keep on moving with the particular speed with which on which the alternating voltage is being applied between stationary and the fixed electrodes. So mismatch is the basically the whole game behind all this stuff. So again, this is basically stator part, this is the rotor part, and rotor part has some teeth, and these teeth are aligned with this another gear, and then definitely if you mesh another gear with it, and then you can make a proper gear drive, and then you can accordingly drive some other mechanisms in the MEMS. But these are not very popular thing or the normal things in the MEMS, so we don't go for such rotational things in the MEMS. These are all experimental stuff. Practically, we don't have any type of the motor that will be produced on commercial basis for all this stuff. Then you have micro valves, right? So micro valves again are the almost similar type of the mechanism as the micro pumps are there, right? So you have electric resistor heating over here. These are the heaters which when are heated, so they expand. When they expand, so this particular point moves in response to this heated, because when they will expand, so this will go down and this will also go down accordingly, right? So and they when they will when the voltage will be removed, they will get cooler, and when they will get cold, so they will shrink, and when they will shrink, they will up lift this one. So this is the inlet flow. Flow is somewhere over here, and when you remove the voltage, it will goes up, it will go up, and this will allow the fluid to go come inside and then pass through it. And when you will heat them, so it will expand and it will choke this area, and so the flow will be stopped accordingly. And rest are some mathematical and also not the mathematical dimensional parts of this microfilter. Another type of this is basically the electrostatic pump, electrostatically actuated pumps. Again, you have two electrodes. This is the top electrode, this is the chamber, right? And this is basically the electrode on which the voltage is being applied. So when there is voltage is applied, right, so this will basically, sorry, जी. So this is basically the electrode, this is basically the diaphragm, and this is the pumping chamber, this is the low pressure fluid, and this is the high pressure fluid outlet in it, right? When the voltage will be there, applied voltage will be there, so electrostatic force will be generated. When electrostatic force will be generated, this all will move up. When this all will move up, this low pressure, the high pressure, the low pressure fluid will get into this chamber, and when you will remove the voltage, it will go up, this will be closed, and this will be open, and then the pressure, that fluid that was present into this chamber will come out of it. This is the one way valve, so that the fluid in the chamber does not go back into this one, right? So then when it will move up, so it will open this, and the chamber will be filled with this one, and when that voltage will be removed, it will pressurize that particular fluid to get the out of this valve, and then it goes out, and when fluid will be coming out, this valve will be closed. So this is how it will be electrostatically actuated micropump will be working. There are some piezoelectric actuated pumps are there. You have a pipe above top of that. We have the we have the piezoelectric coating, right? So what happens when you we have already know that when we apply the voltage on the piezoelectric, so it contracts and it relax, right? Because we know that when piezoelectric crystal we apply the voltage, it can deform mechanically, right? So when it is deformed mechanically, so you apply a voltage with having certain frequency, so it contract and relax with that particular frequency. It is just like squeezing the tube. You just have a toothpaste tube in it, so you press it, so fluid come out of it, right? So this is basically the flow of the fluid into this direction, and when this piezoelectric coating is applied with the voltage, so it squeezes, it shrinks, it expands, it shrinks, it expands, it shrinks, it expands. So a wave is generated, and since this is a flexible tube just like the toothpaste tube, so it squeezes that particular fluid uh, inside that particular pipe. So this is how this electrostatic piezoelectric crystal will be providing a force which will be allowing the fluid to flow out of it. Again, this is not very important. I mean, micro heat pipes, because heating source is very important for us, right? So what you do, that you will have a pipe having different cross sectional area, right? Like this one. This is the cross section here. This is the cross section here. This is the cross sectional area. So cross sectional area of this pipe is reducing as it is moving from this direction to this direction. So when so you have a once you have a heat sink, another one is the heat source. So for example, you have something that in the gaseous format, not in the gaseous format, that is the liquid format, it will come in contact with the source, so it will be vaporized. When it will be vaporized, so vapor will move into this cross sectional area, and when they will reach at the heat sink, they will give all the heat to the heat sink and again get liquefy. and this liquid will be again going back. Sorry, the direction is this way, right? So gaseous over here, vapors will be moving into this direction. As it is moving towards the sink, it will be liquefy, and after the liquefaction, it will go back to the heat source. And this way, this circle is keep on here it all the liquid will be in the gaseous format, and here it all everything will be in the liquid format after losing the heat into the heat sink. So this is how it keep on rotating inside this pipe. So it keep on removing the heat from the heat source and giving all the heat to the heat sink accordingly. Micro accelerometer. I mean, we will discuss it in detail in chapter 4, I think, where we will go for this all this mathematics of all this micro accelerometer. But here we can discuss it. What the micro accelerometer do? Micro accelerometer generally sense the acceleration. So what you have there? You have a body, that is the body that is vibrating. It can be a machine, it can be anything, it can be an engine where that is constantly vibrating and moving to and fro. Now you put an accelerometer on it. This accelerometer has a mass, this accelerometer has a spring, and obviously this mass, this would have some damping or heat dissipating elements. Since this this particular surface is moving, so when it will be moved, so this mass will move into this direction. When this mass will move, this spring will be compressed, and when it will go down, the spring will stretch. So this is how the mass will be keep on moving into this direction. So equation of motion will be just like a standard equation of motion which we generally write. We say mx double dot plus cx dot plus kx equals to 0. So this is a standard single degree of freedom system having certain mass m, damper d is damper c, and k as the spring stiffness. So mx double dot plus cx dot plus kx is equal to 0. So this is what they have written over here as well. We will discuss in detail. Sum of all the forces equals to mass into acceleration. Newton's second law is utilized, but we will discuss it into detail. These are one of the most popular sensor which we generally use for the measuring accelerometers in the MEMS. So this is I mean this is the cantilever beam accelerometer. So you have a constrained base over here, and on the base you have a cantilever, and cantilever has a piezo resistor, and this is the mass on it, and this is the vibrating base. So when this base will be vibrating into this direction, so this will be oscillating this into this up and down motion. When it will be moving up and down, the resistance of this piezoelectric will be changing, because this is the piezo resistor. So the resistance of this piezo resistor will be changing, and that resistance change in resistance will tell us how much is the basically acceleration is being generated on that. This is again uh, electrode based or the comb drive based uh, micro accelerometer. You have these are the stationary comb drives, these are the moving comb drives, and this is suspended the uh, over the substrate, right? So when the acceleration will come from this direction, so it will move this beam into this direction like this one. So when this beam will move into this direction, so the gap between these two will change. So it will come closer to each other. So resultingly gap will change, resultingly capacitance will change, and that change in capacitance will be related by the indemnity from the acceleration that is coming into this direction on these accelerometers. Gyroscope is a sort of accelerometer, but it has a different sensing mechanisms, right? So gyroscopes are used to measure the angular acceleration instead of linear acceleration. Linear accelerations are being sensed by the accelerometers. Gyroscopes are particularly used to used to sense your angular rotation, right? So it has a very complicated theory. Definitely we will not go into very much detail, but the operating principle is basically the Coriolis force. Coriolis force is basically a sort of fictitious force like the centrifugal force or the Euler's force, right? So what you do, you have three axes, right? X, Y, and Z. One axis is specified for the vibration, so for the velocity, right? So what the Coriolis force says, it says that if a particular object is moving with a linear velocity v and any rotation at the rate of omega that comes along any of the other two axes. For example, this is x-axis, this is z-axis, and this is y-axis, right? So x-axis is the direction in which this particular mass is moving with the velocity v, right? And any rotation comes along z-axis, that is omega. So there will be a force that will be generated into the angular direction that is orthogonal to the moving plane with the velocity v and rotating plane that is omega in the z direction. So orthogonal axes of x and z will be y, right? So a Coriolis force will be generated into the orthogonal direction to the drive axis and the rotational axis. So, so the complexity in this device is that all three axes are basically in the moving phase. This is the axis in which it will be continuously moving with a certain velocity v, and then it will keep on waiting for any angular rotation at any angular particular orientation. In this particular case, it is z. Whenever there is some angular rotation comes against z, so this mass will automatically be moving into the y direction, that is orthogonal to x and z direction, and this force will be sensed, and that force will be related with the angular rotation. So if Coriolis force is 2 into mass into v into omega, so directly proportional to mass, directly proportional to v, and directly proportional to rotation rate with which the body or the object is turning. So if we want to increase this Coriolis force, we need to increase either mass or velocity with which that particular mass will be moving, or the angular rate, because angular rate is related to the sensitivity of the device. So we are only having control either with the mass or with the velocity of that particular mass. So there are different mechanisms that can be generated, like this one. This is the negative direction of that, and this is another. These are all similar type of the different, just showing different sort of configurations of the gyroscope. So as I earlier said that this is the mass. This mass is suspended. These are all springs, and these are basically interdigitated comb drives which can be used for the, because you have one axis specifically for the movement that will be moving with a certain velocity v. So in this particular case, resonator for linear motion generation. So these are basically driver electrodes. These electrode will apply a electrostatic force on the mass, and this electrostatic force will keep on oscillating this mass with a certain velocity. This is basically y-axis, that is the sensing axis, and you have this sort of comb drives over here that can be used. So when out of this screen, this is the z-axis, right? This is the z-axis. This is basically x, y, and z-axis is this one. So when rotation will come along this axis, so this will move this axis this way. So this is velocity axis, drive axis. This is rotational axis. So Coriolis principle says that if x is the velocity axis or the drive axis and z is the angular rotational axis, so Coriolis force will be generated orthogonal to x and z, that is y, and it will move into this one. Now if we put the comb drives over here, so what will happen? It will move into this direction, gap will be changing capacitance will be changing. Resulting, we can relate that capacitance with the angular rate that is coming on to that, right? Here in this one, these are basically the drive electrodes. So when the potential difference will be applied, electrostatic force will be generated, and this electrostatic force will be this is a fixed one, and this is the moving one. So fixed one will pull the moving one with certain velocity v. So this is how we can go for a gyroscope for the micro gyroscopes. So here we end the chapter 2. So you can unmute your mics, and if you have any question we can discuss. Otherwise then we can go for the next lecture, in which we will go for the third chapters to deal with. Any questions now?
No, sir.
No, sir.
और कोई समझ आई है? सुनते ही रहे हो और तो बंदा, अब तो बंदा जो है वो ये भी नहीं पूछ सकता ना.
नहीं सर, समझ आई है.
अच्छा,
यस सर.